Hello and welcome. In this video, I'm going to go over how to use test for analysis of OpenSteadyDevices. But before we do that, you make sure that you understand how to evaluate properties using flow states test steps. Okay, so let's begin by understanding what you mean by open and steady systems. Well, when a system is open means there is mass flow in and out are allowed, and examples of such systems can be plenty. And steady means at a given point the state doesn't change with time. And the examples are like duct flow, boiler tube, water heater, nozzles, diffusers, pumps, tons of examples. These are examples of a single flow open steady state systems. That is, there's one flow going through these devices. But in examples such as mixing chambers or heat exchangers, for instance, there will be multiple flow going through the device. Okay, so where will you find more examples of such systems? I think I have started a number of animations. So before that, how do the governing equations change is shown in this particular animation. If I pause it, you can see that the most general equations are shown here. These are the, I'm sorry. These are the most general equations, mass, energy, and entropy. But as you can see, steady state means there is no rate of change of mass, energy, or entropy. Nothing changes with time at a given point. Therefore, over the entire device, nothing changes with time, and the unsteady terms go to zero. And that's the biggest simplification for steady state. Because the system is open, we cannot neglect the transport terms, so they remain, and therefore the system simplifies in this manner as shown here. The equation simplifies in this manner, and furthermore, if there is only a single flow through the system, there is no summation necessary, and the equation simplifies even further. So in a turbine, in a compressor, in a pump, equations will be very simple, whereas in a mixing chamber you have to take care of a summation. Okay, tons of examples here. This is the energy diagram for an electric water heater. Here is the system, as you can see, simple electric heater, steady state, open system. And as you go to the energy diagram, you can see that J is the rate of flow, J dot is the rate of flow of flow energy is coming in and going out, and we are adding energy through electricity, and some energy might be lost with heat, and the steady state is maintained. There is no accumulation of energy in the system. Entropy diagram, similarly, entropy can be coming in with mass, going out with mass, or leaving with heat transfer. Also, entropy can be generated because of thermodynamic friction. So it's a balance of these terms that make the entropy equation. For further examples, in chapter 4 there are so many examples. This is a nozzle. It shows how the single flow system looks on a TS or a PV diagram. If it's a subsonic gas nozzle, the converging nozzle. Likewise, in a turbine, in an actual turbine, the TS diagram or HS diagram looks like this as the flow goes through, from inlet to exit. In an isentropic turbine, of course, we'll have entropy remains constant because there is no thermodynamic friction inside. So likewise, there are plenty of examples. This is an example of a heat exchanger where there are two different flows. They don't mix together, and the governing equation kind of is slightly different here because we have to retain the two different mass flow as opposed to a single flow system. In case of a mixing flow, similarly, you can see that it's a mixing chamber, two different flows going out, but the system is still steady. And again, the energy, entropy, and mass equation will be slightly different for a mixing chamber. So with that background, let's go quickly make up a problem and solve. Let's say we want to solve a system involving a turbine, a steam turbine. Okay, so we follow the system analysis, open system generic branch, and we go through a single flow device. And a steam turbine will be handled by the PC model. We launch that, and the default page is hands-on examples. You have plenty of videos of separate complete solution of different systems. But in our simple situation, let's make up a quick problem. Let's say steam is coming to a turbine at 1000 kPa and 600 degrees Celsius with a mass flow rate of 10 kg per second. We calculate our inlet state. At the exit, let's say the pressure is 5 kPa and the temperature is 40 degrees Celsius. I'm just picking up almost arbitrary numbers. Of course, the mass flow rate doesn't change. Mass flow rate must be the same in a single flow device. So with state 1 and 2 calculated, you can see that 1 and 2, if I do a constant entropy line, you can see it's not an isentropic turbine. There is some entropy generation must be in this system. So we go to the device panel. That's where you can see it's a steady device. Inlet state you can load, and exit state you load. As a result, now mass, energy, and entropy equation can be solved if either of heat transfer or work transfer is known. Heat transfer is 0 in an adiabatic turbine, and we can find the external work output or net work from the turbine, also the entropy generation from the solution of the entropy equation. So it's a very, very simple example. Likewise, suppose you have a mixing chamber, for instance, then we'll launch the mixing multi-flow device. In that case, you'll notice, suppose it's again the PC model, a mixing between two different, a steam of different temperature. You will see that the device panel will look slightly different. There are two different inlets, and although there are two different exits, you can leave one at state null and just turn one of them on. Then we'll have a state, two inlet state and one exit state. Or we can use this device for a separation flow. For instance, a single flow comes in and two flows go out. In case we have a heat exchanger, for instance, it will be non-mixing multi-flow device. And if you open, let's say we have a gas flow to the system, like a heat exchanger between a hot and a cold gas, then you can see that the flows are not mixing. So you have the inlet 1 and exit 1, and inlet 2 and exit 2, they're separated. So the concept is very simple. You calculate the inlet and exit states as much as possible, come to the device panel, load those inlet and exit states, enter the device variables, maybe the heat transfer is known or the work transfer is known, and then let this equation be solved by the test app, and the unknowns are posted. If a state variable is calculated, it will be posted back here, and all you have to do is to click the super calculate to iterate between state and device panel so that the desired unknowns can be found. More on this can be found on the hands-on example. So I'm just giving an overview here, and we'll let you explore OpenSteadyDevice, which is the backbone of a ton of other test apps in the specific open branch.